Right, I think it's 1:30. I just want to welcome you back again for the second session. So I'm chairing the afternoon session. My name is Untitled Chapter, and I'm the one of the main organizers of the 6-month program. So it's my pleasure to welcome our Christian Schmeiser to talk to us about a continuous model for actin filaments. So.
Thanks a lot for the introduction. Yeah, I'm actually one of the workshop co-organizers, but the other co-organizers asked me to give a talk, so that's what I do. And also I'm different from the speakers in the morning. I'm a trained mathematician, and you see that on the first slide because I put the people I work with on the first slide, not on the last. So that's the distinction between the mathematicians. So let me immediately start with that. Some of this work is, or part of this work is, has to do with the thesis work of 3 present and former PhD students, Christoph Winker, Angelika Mahnert, and Stephanie Hirsch. And there's cooperations with also, again, Dietmar Oelz, also a former student, Nikolaos Fakianakis, a former postdoc, and most importantly, 2 biologists, Vic Small and Michael Sixt. Actually, the cooperation with Michael Sixt has just started, and cooperation with Vic Small has gone over quite a number of years, and it has been absolutely crucial for what I will tell to you, because all I learned about cell biology, or almost all I learned from Vic Small, and he was very patient over the years to listen to my silly questions and trying to give reasonable answers to them. So this is really, I couldn't be in this field without having met Vic and talked to him a lot, so that has been very important. Myself, I have started roughly 10 years ago starting to get interested in questions from biology. Before I've done completely different things. So I think I do not have to explain the title to this audience, and also my first introductory slides I can go through maybe reasonably quickly. My subject is the lamellipodium, and my subject is also one part of the cytoskeleton, which is the actin cytoskeleton. And more narrowly, the actin cytoskeleton in the lamellipodium is very special compared to what it is in other places. So this is one particular relatively small subsystem of the cytoskeleton as a whole I'm talking about. And you typically see lamellipodia when you put cells on flat surfaces, and here you have several movies of this kind: the fish keratocyte, a fibroblast, and a melanoma cell. Ignore the one on the left upper right, that's an ensemble of cells, but these 3. And all three develop lamellipodia. The nicest is the fish fibroblast, who has this big wide lamellipodium, but also the fish keratocyte, but also the fibroblast in front here and the melanoma cell around here have lamellipodia, these thin regions stretching out on a surface. However, that lamellipodia are created is something more intrinsic, kind of. It's not only something which happens in 2D. I don't have a picture now, but there are nice pictures of lamellipodia produced by cells in suspension, where they kind of grow out these leaflets. There are cells which look like lettuces if you treat them in a certain way with lots of lamellipodia. They grow into 3D. However, I will be concerned with the situation on a flat surface, and on the right here you have a textbook picture explaining motion by lamellipodia, protrusion, retraction, and these things you all have heard about. The basic principles of this movement. Of course, this is theory, so and it doesn't explain anything in detail. For making a mathematical model, you have to try to understand what's really going on. And when you ask the biologists, they say, yes, I have a theoretical model for what's really going on. And when you ask, you have big expectations as a mathematician, you think now they will write down the PDEs, but they don't. They draw a cartoon and tell you this is the theoretical model. And you see there's lots of things going on, many symbols characterizing different proteins here. So the filaments in pink, the actin filaments in pink, various kinds of cross-linkers in the middle, some which have sit at branches, some which sit at crosslinks, crossings, some which sit between parallel, more or less parallel filaments. In the back, there is depolymerization going on, depicted by these scissors, and in front, obviously something very complicated is going on because this picture looks very complicated up there. It's not really known in detail what's going on up there, which proteins precisely do what, but what's clear is what's happening there is polymerization. So the monomers, new monomers are added, and it's also clear that there is a protein machinery there which regulates this mechanism. In front is the leading edge. This is just symbolizes the front edge of the membrane, which is stretched around this whole structure, and there is not only this. Now, if you know that these things happen, then there's still the question is what effect do they have? So you need to describe the mechanics, right? For instance, you need to say what material are the actin filaments, what kind of material is that, right? How do they behave mechanically, and so on. And eventually we'll try to model all that. However, again, this is just what the biologist tells you that he thinks is going on. So the question is, can you get more reliable information? And there the group of Vic Small has been one of the world leading groups in imaging this system. And what I will show you now is a movie where the time in the movie will be the z coordinate, the vertical coordinate. So we go through a lamellipodium from bottom. This is below, you see only noise so far, don't stare at it. We are below the lamellipodium, so only when I start the movie you will see something.
What is the scale bar?
The scale bar here is like, I don't know exactly, but it is like 2 micrometers, something like that. Yeah, it's a width of. So we have been going up first, seeing these longer structures. On the way down, we track them. Okay, the green lines, these have been drawn by hand, not by me, fortunately, but by people in the group of Vic Small. And after you have done that, this is 3D information. You throw away the picture. You just keep what you drew, and you can now look at it from various angles and so on, and you really see what the structure of the network is. Okay, so this is very important information. I don't know, for the experts, Vic Small has been involved in a kind of dispute about what the structure of the network is, and I think in the end the story ended kind of with a draw in some way. He had to take back some of the things he said, but some of the criticism he did for other peak imaging which has been done in this system was also justified. So I think it is kind of a draw in the end. Okay. This brings me also to our first contribution as mathematicians. Of course, doing this by hand is a very painful procedure. So one of the first things we did was trying to automatize this. And I don't want this is not the main subject of my talk. I just show you one other movie of the same kind, where now the tracking has been done automatically, and looks like we have done a pretty good job there. It is we're not precisely at ends of filaments or so on. We are not doing maybe as good as a job as it's done by hand, but for statistical purposes or so, and it's sufficient. To prove that, I show you one small part of such a picture, where in green are the hand tracked, and in red are the automatically tracked filament. And you see in this part of the picture we are doing perfect. So that's not the same everywhere. Okay, anyway, so that's the kind of information which we have. So now the idea is whatever kind of modeling we do, that is an important point for me, is has to respect that. There shouldn't be anything in the model which contradicts these basic pictures or consequences you can draw from them. At this point, I want to make a very general statement concerning mathematical biology, right? If you understand how this, what's really going on here, polymerization on one side, depolymerization on the other side, adhesion holding on to the substrate, then you see the basic principle of the movement is like a tank moves, okay? Now, as soon as you have understood this basic principle, you could take your mathematical model for a tank, make the tank material a little more flexible, right? Say make it softer, have a few parameters you can play with. I'm pretty sure you can reproduce cell shapes, which you see under the microscope. The question is, have you learned anything from that? Okay, so I just posed the question. It's an answer. So, but that this kind of thinking is what the basic motivation for what we do. With trying to really look at what's really going on in detail and try and come up from there to systematically produce models. Okay, so this was my introduction. Now the rest of the talk is structured in 3 parts. First, what I aim is, the main part is this section 2, where I introduce the model with which we compute with. But as you saw already, this is we are trying to model a very complicated heterogeneous structure. So this model contains a number of submodels. So what I will do first, I will introduce several of these submodels. Some of them we have not developed ourselves. We have taken from literature. Others we have developed ourselves. And in the end, in the second section, I will show you how we have combined all that. And finally, and that in real time, the longest distance was from 2 to 3. The model is a very is a new type of mathematical model. So there's no theory, no numerical simulation methods, nothing. And to develop a stable simulation procedure for that was a step also which took a long time. And only rather recently we can produce the nice movies, which I will show you in the end. Okay. So modeling ingredients. Several aspects. In all this, in all this, there's some basic mechanism which occurs over and over, which is the dynamic linking. What do I mean by that? For instance, adhesion by integrins. You have adhesion to the substrate. In relatively fast-moving cells, like the fish keratocyte, under the lamellipodium, the linking to the substrate is a very dynamic process. Links are built and broken all the time. The same is for cross-links between crossing filaments. Filaments move along each other while when they get close, there is a link. After a while, the link gets broken again, and so on. First thing we want to do is we don't want to describe these processes in detail, right? Molecule per molecule. We want to get the macroscopic effect of this. So we try to do mathematics on that. So I walk you through this model rather shortly. In order to, when you have so you move across a substrate, you throw an anchor, right? You throw the anchor just where you are. Then, say the anchor rope is elastic, you keep moving, it gets stretched. That holds you back. You wait until you stop, then the anchor might break, okay? Then, if you say the wind blows on the water, you move a bit more, you throw another anchor, okay? So that kind of system we want to describe. In order to know how much one anchor is stretched, you need to know when you have thrown it. How long ago have you thrown it? So what we do as mathematicians, we write a H-structured population model for the anchors, for the anchor distribution. And that is this first equation. The left-hand side is just describes the aging of the anchors, that they get older. The right-hand side describes the Poisson process where the anchors get ripped off at a certain rate. Okay? Then the boundary condition, right? At age equals 0, this describes how you throw the anchors. And you say you only have a certain amount of anchors available. This describes this term in the parentheses, right? If the total number of anchors, this is scaled, is the maximum number, then you cannot throw any new anchors anymore. And finally,
I understand that rho is the density of anchors. Is that the density of engaged anchors?
It's the number of engaged anchors.
Okay.
Sorry.
Thank
Yeah. distributed over their age. Okay. So now
Sorry, A you call the
age of the anchor. It means how long has it been engaged.
But if I think about mechanical element, it would also be the elongation of the anchor.
That depends on how fast you move.
Yeah, but if I
Yeah.
move in a constant velocity, you could translate time into
Right? This exactly is described by this term here. If you move with constant velocity, x is the position with respect to time. If that would be linear, right, as you said, then it would be proportional to a. Okay? But in reality, it's this, since you don't know how fast you move. Okay?
Do you assume that your anchor anchors anywhere you throw it?
Do it.
You assume that your anchor attaches anywhere you throw it.
Well, for all these, I assume there is a homogeneous distribution of ligands on the substrate, which so that whenever I want to throw an anchor, I find some at a certain rate, of course, right? That goes into this beta. Okay, when if there are only few, the beta is smaller. If there, yeah, of course. This model could be and is in for certain applications we use it extended in various ways. Okay. An interesting one is, by the way, not to use a constant breaking rate, but use a breaking rate which goes with stretching, which is a very natural thing. An anchor which is stretched more breaks more easily, but that all makes the story immediately more complicated.
it becomes nonlinear.
Right, exactly.
Question, I mean, are you going to do signal perturbation analysis?
Yes, this is why I put an epsilon. Thank you. Thank you. What's the meaning of the epsilon? It's written here. It's the ratio of the lifetime, a typical lifetime of an anchor compared to the time scale I'm interested in, which is much bigger, right? This is why I'm doing this. Okay. Now let me finally explain this third equation. F is the force acting on my moving body. Okay. And here is the force, the elastic force, which comes from the anchors. It's the how much is an anchor stretched. Now it's like each anchor is a linear spring. How much is it stretched? And all these summed up with multiplied with the density. Okay. So this term is the force, total force the anchors exert, and this is the force, given force I apply, right, when I pull. Okay.
As a physicist, I worry about units.
About what?
About units.
About units. This is non-dimensionalized. Sorry. Yeah. So this is not. This is completely. This is non-dimensional. So this is why I also have this non-dimensional parameter epsilon here. And for instance, there is an assumption in here, which is that the springs are rather stiff. This is why I have this 1 over epsilon. There's a scaling assumption in here. Right? If the springs are not very stiff and they keep breaking all the time, they don't have any effect at all. So in order to get a macroscopic effect, I need to assume then that they're very stiff. Okay. Now there is one big disadvantage for using this model. It is in this term here, which is a delay term. You always have to look in the past, right? If you want to, if you do this 1D thing, just 1x, just a real quantity, that's no big deal. You can easily do numerics for that. However, for the x here, we have that everywhere in our lamellipodium, that kind of thing, right? We have adhesions everywhere, crosslinks everywhere. So that would create a very expensive model to simulate with. So this is why we do this, what we call macroscopic limit. Let this epsilon tend to 0. You see in the limit, this is almost like a derivative, and it will be a derivative in the limit. Okay. So now, if you pass to the limit in this model, you get something very simple, and you could have written that right away. We get just this is the important equation here. You just get linear friction. So this whole right-hand side just becomes a number times the velocity, so it's just linear friction. So this is one way to derive linear friction. Okay. The good thing about it is, I have for this friction coefficient here, I have an explicit formula here. Sorry. First, I can compute this rho explicitly, and then I put it in here, so I get an explicit formula for the friction coefficient in terms of what happens microscopically. In terms of this was the building rate, the beta of the crosslinks, the zeta was the breaking rate. Okay, so the good thing about this model is I can use it in two ways. I can use this coefficient here as a fitting parameter, as that would what you would do most of the time. However, if I have some microscopic information, some in vitro experiments, how really what the detailed reaction kinetics is, then I can use this here. Okay. The whole story is old from the formal point of view. This guy Schallamach in the 60s has worked on rubber friction and basically done more or less the same. The story is surprisingly complicated from a mathematical point of view, and these two people, Vuk Milicic and Dietmar Oelz, a former student of mine, have written a series of papers already, and this is one of them trying to make all this story mathematically rigorous. Okay, that's surprisingly not easy at all. So that's one ingredient of the modeling. It will be used wherever we have cross-links or linking of any kind, adhesion, any kinds of links. Next story. How long do actin filaments get? This is a very old story. A prominent person having worked on that is sitting here, right, Hans? What's length distribution of actin filaments? So here we didn't have to invent anything new. In particular, what we took was just something reasonably simple with a small number of parameters. Okay, and the story is the following: what contributes to the length of a filament? Polymerization on the one hand, depolymerization on the other hand. For depolymerization, there are various possibilities. The one which is seems to be the most important is what's called severing. So filaments are cut. At some point, you have an active end of the filament where it polymerizes, and at the other end, somewhere along the filament, the tail is cut away once in a while. The protein doing that, the most important, is called gelsolin, for instance, one of them, which is doing that. So now we write a model which just describes what I said. This is a stochastic process, right? Filaments grow. That is not stochastic. That is deterministic, but the cutting is stochastic. Okay, it's a Poisson process for the experts. Yes.
Have you got capping proteins in there as well?
Yes. Capping comes. Is that at this point we talk about filaments when I tell you in particular what we will do as soon as filaments get capped, we basically take them out of the story because they are not active anymore. Okay, so this is about active filaments. So there is no capping yet. Okay.
In principle, I mean, the way I picture this, it's the same thing. I mean, you have severing on the back side and capping on the front side. It's
yes.
a Poisson process. So you have the same thing double.
Yes. However, the process in the front, at least that's an assumption, right, can be seen as deterministic, right, because it happens really a lot, right? There's many more. The process of adding one monomer, right, happens much more frequently than the severing in the back. Okay. So that we consider this process in the front as a deterministic process, just growth with a certain speed. But this is a detail. It's not so important. We could also model that stochastically.
I was thinking about the capping. The capping is a Poisson process.
The capping will be a Poisson, but
to the severing.
right. Yeah. Sorry. Yeah, the capping. But that you will see. We'll do it that way. Yeah. Okay. Now. I don't know how to, I don't want to go through the equations too much. Again, the left-hand side, it's a density, it's an equation for the density of filaments of a certain, with respect to the length, okay? And the left-hand side, the left-hand side describes the increasing of length by the polymerization, and the right-hand side describes the capping process. Maybe it's well understood here. You lose filaments with a rate which is proportional to their length s, right? Longer filaments can get severed more easily, and you gain new filaments of a certain length by cutting longer filaments, right? This is why you go from s to larger length. Okay. Now the interesting thing about this model is it's simple enough such that you can compute an equilibrium state explicitly, which is written here. Okay. And maybe for those who don't want to look at the equations much, they only look at the last one. From these, you can compute the mean length, which where the formula is very plausible. The mean length is bigger if the polymerization speed is bigger, and it gets smaller if the severing rate gets bigger. Okay? And what we will later really use is this formula here, this length distribution. Okay? Again, for the model in the end, it will not be very important which of these formulas, which of these possible formulas we precisely use, but that's one of a reasonable one which we use. Okay? So, next step. Something the biologists in this business usually talk about quite a bit, is so-called lateral flow. Actually, from a mathematical point of view, it's something very simple. The picture on the left up there has been drawn by Vic Small to explain what's going on a long time ago. So there are filaments, and typically they are inclined to the leading edge, right? They are typically not orthogonal to the leading edge, but at some angle. I will talk about the question why and so on in a second. So when the filaments polymerize, right, their end moves either to the left or to the right compared to the leading edge, okay? And that process is called lateral flow, right? If you just look at the leading edge and follow it as it is moved forward, and then track where the filament ends go, right? You see some of them go to the left, some of them go to the right. That's called lateral flow. Now, what we want to do, what I want to do here now is to write a small submodel just for what happens to the filament ends. And now comes what you, we had talked about polymerization already and the severing in the back. Now come the processes which happen at the front. And which processes happen at the front? The capping, which was already mentioned. So filament ends get deactivated, which means they don't polymerize anymore. They fall back as the leading edge is moved outwards, so they don't play a role anymore. But the other thing is nucleation of new filaments, right? If you would only have capping, you would run out of filaments eventually, so you need to nucleate new filaments. And this is actually now the subject of this dispute I mentioned earlier, and now it is, seems to be agreed upon that new filaments are created by a process called branching. They branch off from existing old filaments. Okay? Now, if the situation is roughly like it is drawn here, then there are some filaments moving to the left, other filaments moving to the right. Branching, now our assumption will be branching produces right-moving filaments growing off from left-moving filaments and the other way around. But there is a lot, there is some support for that experimentally, which I will come back to in a minute. Yes, so I want to describe, what I want to describe now is the number of, or the distribution of filament ends along the leading edge, taking into account the lateral flow that they move around, the branching, creating new filaments, and the capping, throwing away filaments. Okay? Writing a model for that is in principle rather straightforward if you know one thing, which is the speed with which filaments move along the lateral flow. Okay? In reality, of course, that depends on a lot of things. It depends on what's the, or in principle on two things. It depends on what's the angle between the filament and the leading edge, and it depends on how fast does the filament polymerize. Okay? This is a complicated question. It depends on the whole geometry of the cell and so on. Later in our full model, this speed, this lateral flow speed, will be part of the solution of the problem, of a bigger problem. But now for the small submodel, I assume it is given. So the flow speed is given. So I have two equations, one for the right-moving filaments, one for the left-moving filaments. And U and V are the densities of barbed ends of right-moving filaments, of barbed ends of left-moving filaments. And C is the speed, and I make a simplification that both move with the same speed at a certain position. Okay? However, the speed can depend on the position where they are and so on. On the right-hand side, I write branching and capping. Okay? So you see the branching is proportional. Branching, new creation of new U filaments, of new right-moving filaments, depends on the density of left-moving filaments. First order reaction. However, now we build in one thing. when you create the branch, you need a protein which sits right at the branch, which connects the two filaments. Or actually, it's not a protein, it's a protein complex called ARP23. I think it was mentioned already in the first talk in the morning. So you need this ARP23. So one assumption we make here is that the whole process is limited by this ARP23. So we say that the branching rate is also proportional to the density of ARP23, A. Okay? And now we need to describe also the dynamics of this ARP23. And the dynamics is here. We say first it is recruited to the leading edge from the cytoplasm, or to the membrane from the cytoplasm at a constant rate, that is this C-reg. Okay, we say that there is also the reverse process, and if these two processes are in balance, there is A naught is the equilibrium density. Okay, but on top of that, ARP23 is used by the branching. Okay, so the idea is there is a kind of treadmilling of ARP23, right? It sits at the membrane. It is built into branches. It's by the polymerization of filaments. It's moved away from the membrane. Eventually, the structure breaks. ARP23 becomes free again, diffuses in the cytoplasm, can be recruited again, and so on. We don't describe the whole circle, right? We don't describe what it does in the cytoplasm. We just describe this part on the membrane.
I'm puzzled, or maybe I'm thinking too complicated. The point is, you basically assume you have two types of filaments. They move with the same speed and they move apart, right and left.
Yeah.
Now, how does a branch know to branch off to the left side of a right moving filament and not again to the right side?
That's a very good question, and the answer that I can give you a half-hour answer or a 5-minute answer, so I try to give a short answer. Basically, the first information is branching only occurs right next to the barbed ends. So that is something you see in the pictures, right? It is really, so that is where the branches are started. Now, for each filament, now if you think in 3D, the ARP23 produces a certain angle between the filaments. Okay, so what you really have is a whole cone of possible directions. Okay, now the question is which direction is chosen, and so if you choose a direction where you don't point towards the membrane. If you are not connected to the membrane, the answer gets long. I was afraid of that. So I have to say something else again. A typical assumption is that the filaments, or at least that's the assumption we use here and which has also been verified pretty well, is that the filament ends are tethered to proteins on the membrane. Okay? And this tethering, the idea is that this tethering protects them from being capped. Okay, so that means when a filament is not tethered to the membrane, it can get capped easily. Okay, so our assumption is we do not need to talk about this kind of branching at all, because the filaments will get capped immediately. We don't need to talk about them; they don't contribute. Okay, so we only need to talk about branching which goes towards the leading edge. And since in the 2D picture which we have here, there's only two, my cone is only two directions, right? I can only pick the one direction which goes towards the leading edge. Okay, is that a reasonable answer? Okay. There is more to that story, but in particular in 3D, but it's
a really complicated subject, okay?
Yes.
I don't think there's really experimental evidence that those, I mean, the problem is a gradual thing, okay? It's not that you are either on the right plane or you're completely off. You could be a little bit off from the plane.
Yeah, he is already touching the 3D subject.
Yeah, exactly.
Well, life is 3D.
This is. I have a whole talk on that because we have worked on that, but that's not the subject here. It's a complicated story. Okay, what makes it to stay in the plane? Okay.
But if you stay in 2D, I think the answer is relatively simple. I mean,
yeah.
If you branch to the wrong side, you're just lost to the system.
Right. That was the shorter way to express it than I did. Yeah. Okay. Anyway, so that was that. But where was I? Yes, the dynamics of of the ARP23 density brings in this extra equation here, right? ARP23 is used up here. Now, in order not to let the model get too complicated, we make an assumption where we actually, which is rather wild assumption. We don't have any experimental evidence that is really true, we assume that the ARP23 dynamics is much faster than the branching and capping dynamics. Okay? We assume that this recycling of ARP23 and to the membrane, in particular this process here, right, goes much faster than the branching and capping. This is just honestly really an argument to simplify the model. Okay?
What does that really mean? That the ARP23 doesn't stay attached to the filament from which it
No, it does not stay attached to the membrane. It is ARP23 first gets attached to the membrane, and then there it's used for branches. Okay, and the attachment and detachment from the membrane we assume is a process which goes very fast. Okay, compared to a typical ARP23 molecule gets attached to the membrane, detached, attached, detached, and only once in a while it gets used in a branch compared to that. That is the assumption, okay? So when you make this assumption, you can make a so-called quasi-stationary approximation in the A equation. That means throw away the time derivative of A. Actually, this can be more justified by introducing an epsilon like I had before, but this would take too long here. Then this just becomes an algebraic equation for A, actually linear. I can solve it explicitly, put the result into up here, and in the end, I get a model like this. Okay? Actually, a model very close to this has been written down already by the group around Alex Mogilna. I think they more or less just wrote it down. We tried to make a story around it. The model they had is actually a little different than this. Okay? Little models like that are nice for mathematicians. You will see in a second. I just say one other thing. Now you have this model, the x variable along the leading edge, right? This is a 1D thing. The question is, what's the whole geometry, right? And now we consider two situations. Typically one where the lamellipodium edge is kind of a bounded thing, right? Has one end and has two ends, which is the typical thing in the fish keratocyte, or where the lamellipodium goes all around the cell, right? There are cells which do that too, okay? Where you have a lamellipodium all around. From a mathematical point of view, you use here either so-called Dirichlet boundary conditions or periodic boundary conditions. For Dirichlet, it just means that no left-moving filaments come in from one side and no right-moving filaments come in from the other side, basically. Okay? Now you have a complete mathematical model. You can do mathematics on that, and I don't want to talk about it much because I'm running out of time. Basically, the question you ask, is this model good enough to produce a stable distribution of barbed ends? Okay? And the answer is yes, it does, conditionally under one condition, which is rather obvious. The branching rate has to be big enough compared to the capping rate. If you do too much capping, you will eliminate your whole system. Things will run out. So, and this ratio between branching and capping is encoded here in this parameter little alpha. So when that's too small, the densities go to zero for large time. If it's large enough, then the densities go to some stable distribution. Okay, maybe I don't draw anything. So that's that's for the model with the given lateral flow speed. Okay, later, as I said, the lateral flow speed will be computed as a result of a more complicated model. Next story. Rather simple in principle from a mechanical point of view. Actin filaments, this term persistence lengths has been mentioned already. So actin filaments want to be straight in principle from a mechanical point of view. There is some resistance, but you can bend them, and there is some resistance against this bending. Okay. Our model will be in the end, what we call a quasi-stationary model. So all forces in the system will always be in equilibrium. Okay? So we will, when you apply a force to say one filament, right? You push it from the ends. It will take some deflected state. We don't describe the dynamics, how it goes from to the deflected state, or how the deflected state changes, we always say it's in equilibrium, okay? So the idea is we are biology, everything is very friction dominated, so we can assume that this is the case. So, so there is we just need to write the mathematical formulation for that. So we describe the filament as a curve, and then write some kind of potential energy, which is corresponding to bending, and we minimize that. And what we choose is this Kirchhoff bending energy. Okay.
Can I ask a question?
Sure.
So is bending really relevant for the lamellipodium? I mean, the point is that the persistence length is 10 micrometers, and there's a lot of capping. So you expect it to be only relevant if there's little capping.
That's a valid question, right? It is still, I could say yes, right? We are actually sometimes working with models with rigid filaments. Here we put it in. There are effects where you want to have bending, although I have to confess that we are not there yet. For instance, one situation is when a filopodium grows out of the lamellipodium, right? Then you see filaments which go into the filopodium like this from the sides. So that would be an example. Yeah, it's not what we do yet. So for most of what I'm doing here, you're right, but we just wanted to have it in. Okay.
So what is causing the bending? So far, all I see is filaments growing at the membrane, but I don't see interaction between them or...
No, there's all these... I'm not done with the modeling yet, but you remember the cartoon from the beginning where there was this cross-linking and so on, right? Creating friction and so on, that will cause the bending, okay? There will all be all kinds of forces acting on the filaments, okay? So, now if you just look at that, then you can write a model, say, for one mathematical model for one filament, which is deforming in time. Actually, now I'm not doing what I just said before. I'm very well look at the time evolution. However, now the time evolution here comes from friction. I don't want to spend the time to explain the details of the model. I just tell you what the experiment it describes. Take an actin filament or something flexible which want to be straight but which can be bent. Put it down on a 2D surface, right? Assume it stays there and assume there is friction with the surface. Okay, and then just watch what happens. Okay, of course it will straighten out. There is again some mathematics to be done. You write the model for that process. The model is not so simple because you allow large deformations of the filament. You allow it bent in a wild way. What you want to say basically, or what you want to prove again mathematically is, does it really straighten out? Okay, and again there has been some work which proves that it really straightens out after a long time. Here you see a numerical simulation of a toy problem, right? On the top you have the filament bent wildly, okay, and then it stretches out. The process from the first to the fourth goes rather fast, and then it gets slower and slower. So you would have to wait very long until it really gets straight. Okay. Yes, actually there is an interesting mathematical question which is open here, which is what is this angle, this direction at the end? Can you compute this angle which it has at the end from this initial form? I don't know the answer. I cannot. Okay, so that's an interesting problem. Okay. In mechanics, people with some experience in mechanics might think of things like conservation of angular momentum or so on, but this process doesn't have that. Okay, so it's not. So it's a difficult question. Okay, now I'm done with my section on preparations on submodels. Now I try to get to the full model, and so the first thing is I show you some experiments, and I have basically shown you already before. What do I want to tell you with this slide? You have seen these cartoons, and they always had these two families of filaments, right? One moving to the right, one moving to the left. Question, is that true at all? Okay, is there some truth to it at all? And here I want to show you that there is some truth to it, right? You see an electron tomogram on the left. Actually, it's the whole information, the 3D information added up. You see lots of filaments in all possible directions, right? So it's not so clear. However, with a little bit of goodwill, I guess you see that there is quite a number of filaments going more or less horizontally, a little bit up to the left here, and another group of filaments going more or less vertically a bit to the right when you go up. Okay. Of course, now you can track the filaments like we did. Now this is the result of the tracking. And after you've done that, you just do statistics of the directions, and what you get is such a distribution. Sorry. Wow.
Yeah, time is flying.
Sorry. Yes. Okay. So. Okay. Thanks. You get this distribution, 2 peaks. Okay. Now, these I want to use as argument that we really can work with these 2 families. Okay. We concentrate. What we do is we divide here. Concentrate all the filaments, one group all here, the other group all here, and that will be our model, our idealized model. Okay. Well, I also have to confess that this is not always the true. It depends somewhat on the stage, on the movement stage of the cell. Okay.
What controls the distance between these two?
Thank you. The distance is very close to the angle this up-to-3 molecule produces at branches. Okay. So the distance between the 2 is created by the branching. The distance between the 2 angles. And that they are symmetric about vertical, that is the argument that the branches always occur quite at the top, because then the 2 filaments grow with the same speed, and that makes a triangle like that where the angles are the same.
Does bending energy contribute to that?
Bending, no, does not contribute to that. In the beginning, this is all rather rigid, right? Okay, so, sorry, I have only 5 minutes.
Go ahead.
So now we put all this into a model. I will not show you the equations because I will run out of time. I just show you what the model basically does. Right? It has, say, in a situation where lamellipodium goes around, it has these 2 groups of filaments, and the assumption will be that all the filaments of one group are locally parallel to each other, and the others of the other group are also locally parallel to each other. Okay? They can bend, they can deform, they have subject to all I said. Okay? And we put in all the models I showed you, the friction models for this, for the relation, for the adhesion to the substrate, and also for the relation between the 2 filament families. They slide on top of each other, basically, because of the crosslinks. And then there are several other things. In particular, we can choose, for instance, the polymerization rate different at different places along the leading edge. Okay? And if we do that, in equations, it looks very ugly. This is a kind of new type of PDE for the PDE specialist. New type of PDE is said a little too much. It has some, included this equation for the beams which you had before, but then there are some other terms where I don't have time to explain them, which address the cross-linking and other effects. And boundary conditions, is something which what happens at the leading edge, what happens at the inner end of the lamellipodium, where there we apply certain forces. So sorry, that was.
I know that we're running out of time.
Yep.
I'm curious, what is new about this PDE? I mean,
well, it is you could say it's a family of beam equations, but distributed beams. So there are 2 of these systems for both families. Okay, so the new thing it is that there is this it's beams which are coupled in the other direction, right? So it is new. It has parts which are not new, but the combination is new. Okay.
But mathematically, I would solve it this usual finite element methods or whatever. Except
that you have 4th order derivatives in one direction, in this S direction. That's the direction along the filaments. only first order derivatives in the orthogonal direction, yeah, that's what we do. We take a special anisotropic finite element method with different ansatz functions in the two different directions, basically. That's it. But then the whole story comes with a number of constraints. For instance, one thing I didn't talk about at all is this, that we assume the filaments are inextensible, which produces a constraint, and others. So that makes it complicated.
Where does the lateral interaction come from, you mentioned?
The lateral interaction first comes from the second line in these equations, which is a pressure term, which comes from Coulomb repulsion of parallel filaments, and then it comes in an indirect way by friction with the other family. Okay. So, sorry. Now let me at least show one or two movies at the end. So let me show these two here. We start in both cases with round filaments. We assume there is a chemotactic signal coming from the right, and correspondingly we increase the polymerization speed to the right compared to the left. Unfortunately, this is very light and doesn't see much. It's too bad. What you should see is, do you see something moving at all? No. So what you get is a wider lamellipodium on one side than on the other because of the increased polymerization speed, and that makes the cell move. What you almost don't see, you see it, that they're very different shapes. And the different shapes come from the fact that in one case we say the chemotactic signal is translated into increased polymerization speed on a long arc, almost half the cell, whereas on the other hand it's just on a short piece, right? We don't really model the signaling network here. We just kind of predict possible outcomes of the signaling network, and we just want to show that it leads to very different shapes of cells. Okay.
On the bottom picture, you have the polymerization localized.
There's polymerization everywhere, but it's increased, localized, more localized. Whereas in the other picture, it's almost it starts on the semicircle. It's almost half the cell, where it
How
is
do you
increased.
explain the global shape?
Well, it's all forces acting together, right? One important question is, why does the cell remain of finite size? What we do is a model for actin-myosin interaction in the middle of the cell by basically pulling at all the internal filament ends. We compute forces which pull on the filament ends, and that is a model for the actin-myosin contraction in the middle. This is what keeps the cell size finite, basically. Okay. Maybe, sorry, one more I like, which is this one, and then I stop. People make experiments, several people have done experiments with prepared substrates which are adhesive in some regions and less adhesive in others. So this is a substrate where the pink region is adhesive and the white region is much less adhesive. Okay? What you see is the cell, because of this effect I just described, being pulled together, it stays away from the region where it doesn't adhere. Okay? And that is exactly what you see in these experiments. Again, we have a signal from the right, so the cell wants to go from left to right, and it just tries to stay away from where it cannot adhere to. Okay, thank you for your attention.
One quick question. Okay. Yeah.
I would have one. So, I mean, something you put in by hand is the symmetry between left and right going.
Yeah, but that I only put in my baby model. That is not in the full model. In the full model, the directions, the simplifications, there's only two directions. But what these directions are, that develops out of the computation.
Because you know that there's this possible structure which is a minus 70, 0, plus 70. Okay? And I wonder if you can get this in your model.
No, I have only two directions. I would need a third. Yeah.
But this is a realistic, I mean, it has been shown to exist at the site.
I agree. But my answer is you have to compare this model to other continuum models which are used in this field, and they are usually isotropic, right? They don't have directions at all. So,
Yeah.
Let's thank him again.